In the previous slides, I drew the mathematical model in a specific form. The model consists of many layers arranged one after the other. The input passes through the first layer, and then the second, and then the third, etc., with each of the layers themselves being a simple mathematical function. So the entire model consists of a function, of a function, of a function. You get the idea. The diagram depicts a mathematical model called a neural network. There are other common mathematical models used in machine learning: linear methods, decision trees, radial basis functions, ensembles of trees, radial basis functions, followed by linear methods. The list goes on. But we are talking about neural networks. Traditionally, neural network models didn't have this many layers. Neural networks date back to the 1970s, but they used to have only one hidden layer. The reason had to do with, number one, computational power. Training deep neural networks with lots of layers, takes a lot of computing power. Second reason they had only one hidden layer, availability of data. As you add more layers, there are more and more weights to adjust, so you need lots of more data. And the third reason why you had only one hidden layer, computational tricks. It turns out that if you just add layers, you will run into some issues. The neural networks will take a long time to train. Some of the layers will become all zero, or they'll blow up and become all NaN, or not a number. So the research community had to develop a number of tricks and techniques to get deep neural networks to work. So in the last few years, neural networks have proven themselves to be the best or near best in a wide variety of tasks, even tasks that used to be thought to be unsolvable with machine learning. Neural networks have enabled dramatic improvements in really hard problems like language translation, image classification, speech understanding, etc. And they work just as well or better on structured data problems as traditional machine learning methods, such as support vector machines or boosted or bagged decision trees. And you can see this at Google. The use of deep learning at Google has accelerated rapidly. We had pretty much no deep learning models 4 years ago, and now we have more than 4,000 deep learning models within Google. So, in this specialization, we will use neural networks almost exclusively. We will start off on structured data problems, and once we know how to build an end-to-end pipeline, we will take that knowledge and show you how to do image problems and sequence problems and recommendation systems. But look again at this graph. 4,000 plus models. How can there be so many ML models? Well, ML is part of pretty much every Google product out there. Whether it's YouTube or Play or Chrome or Gmail or Hangouts, they all use machine learning. It's not that there is just one ML model at YouTube. There are dozens of ML models per product. In my experience, this is something that takes some getting used to. You might look at a business problem, say how to forecast whether an item will go out of stock, and think of it as a single machine learning model that you have to build. But in practice, to forecast whether an item will go out of stock, you will have to build many machine learning models to solve the problem. You might have to break this problem down into smaller problems based on your knowledge of the business. For example, your first model might be to predict the demand for the product at the store location. And your second model might predict the inventory of this item at your supplier's warehouse and at nearby stores. You might need a third model to predict how long it's going to take them to stock your product, and use this to predict which supplier you will ask to refill the shelf and when. And of course, all these models themselves might be more complex. The model to predict the demand for milk is going to be very different from the model to predict the demand for dry noodles. And the model for restocking electronics is very different from the model for restocking furniture. There is not one ML model, there are dozens of ML models per product. This being a teaching course, we will show you how to train, deploy, and predict with a single model. In practice, though, you'll be building many machine learning models to solve a use case. Avoid the trap of thinking of building a monolithic, one model solves a whole problem solutions.